The topics of today are dot products and cross products. So these two products are different ways of combining two vectors to get a new object. So we start out with the dot product. So the dot product between two vectors is a number. So you take two vectors and the output is a number. If you have a two-dimensional vector, you just take the first component of the first vector, first component of the second vector, multiply them, and then you add the product of the second component of the first vector times the second component of the second vector, like this. And if you have two three-dimensional vectors, A and B, then it's just A1 times B1 plus A2 times B2 plus A3 times B3. So the dot product is a way of taking two vectors and getting a number out. And you just do it like this. So here's an example. Use this vector here, so it's 1, 2, 3, comma 1, 2, 3, right? And the other one is minus 2, comma 4. To find the dot product, the reason I have parentheses here is because you might end up with a minus in front. 3 times minus 2, right? Plus 3 times 4. You can try changing this, maybe making it negative as well. So right now we have 12. What did we have before? It was 3, 3, right? Come on. 3, 3. That was 6. So for some reason this is a bigger number. We'll discuss a bit why that is. I can just indicate that it has something to do with the fact that right now the two vectors are pointing more in the same direction, right? Now they are more or less perpendicular. Now they are perpendicular. Now it's 0. And right now they point in opposite directions, right? Clearly also the length plays a role. So this was 3, 3, right? If I now take 6, 6, I get something twice as big, right? I double it. Double it with the vector also means doubling the dot product. So we have a theorem. So for all vectors A, B, C and scalars R, one has that if you take the dot product of a vector with itself, you just get the square of the length. So you can take these two pointing in the same. Oh, let's make some other choice. This one and this one. We've seen this example quite a few times. The vector 4, 3 has length 5, so we get 4 times 4 plus 3 times 3, that's 25, that's the square of the length, right? Then there's a theorem saying that it doesn't matter in which order you have the vectors in the dot product, so now it's what was it before? I think it was something like this. Right now it's 3, 3 times minus 2, 4. We could also do it the other way around. And the result is still 6, right? Then there's a result more. If you take the dot product of one vector with the sum of vectors, it's the same as taking the dot product of the one vector with each of the two vectors individually, then adding. And scalars respect the dot product in the sense that it doesn't matter in which order you multiply. You can either first scale a vector and then take a dot product. You can take the dot product and then scale, or you can actually choose to scale the other vector instead.